Let us recall fundamental theorem of calculus part 2. Part 2 told us that if you want to take the integral of f of x in an interval from a to b, and if we know the antiderivative of f of x, let's say the antiderivative is this capital F, then the integral would just equal to this difference in antiderivative. So here, if you think about this relationship as the integral of, since f of x is equal to the derivative of the capital F, if you think this as integral of capital F prime equals to capital F of b minus capital F of a, we get this following theorem. So we call this the net change theorem. The integral of the rate of change of a function. So we know f prime of capital F is the rate of change of capital F. So the integral of rate of change of capital F is going to equal to the difference, the net change in F from A to B. So there is several applications of this theorem in different areas. Let us look at a few of these. So in this first example, say V of t gives us the volume of water in a reservoir at time t, and we're pumping water into this reservoir. So the integral of V prime then is going to give us the change in the volume of the water. The second example, suppose C of t gives us the concentration of a product in chemical reaction at time t. Then C prime is called rate of reaction. Then integral of rate of reaction is going to give us the net change in the concentration of this product. And we're familiar with this last example from the previous video. Suppose V of t gives us the velocity of a moving object at time t, and S of t is the position function. Then we know that velocity is the antiderivative of the displacement function. Then by the net change theorem, we can say that the integral of the velocity function is going to equal to the net change in position. In other words, it's going to give us the displacement. With this last example, we should be a little bit careful. So the displacement, which will be the integral of the velocity, is going to be different than the distance traveled. So if your velocity function is getting both negative and positive values, which means that the moving object is moving in negative direction for a period of time and then changes its direction and is moving in a positive direction, then the distance traveled is going to be not equal to the integral of velocity, but it's going to equal to the integral of the absolute value of the velocity. Let us try to emphasize the difference between displacement and distance traveled in this example. So we're given the velocity function of a moving object that's moving along a straight line. So the velocity is given by t squared minus t at t seconds. And let us say that the unit for velocity is meters per second. In part A, we want to find the displacement in the first 2 seconds. And in part B, we're going to find the distance traveled in the first 2 seconds. So here, these two values are going to end up being different because if you look at the velocity function, the first second, let us say this is let us say this is t equals 1. Let us say this is t equals 2. So the first second, the velocity is negative, which means that the object is moving in the negative direction. And from t equals 1 to t equals 2, the velocity is positive, which means that the object just turned around and start moving in the opposite direction. So here, if you want to find the displacement, the displacement is going to be the integral of the velocity from 0 to 2. Okay, so here the integral of velocity v of t is going to equal to like the negative of this area plus this area. So let us calculate this. This is going to equal to 0 to 2. The velocity function is t squared minus t. So let us calculate this. By fundamental term of calculus, we know how to calculate definite integrals now. So we just think about an antiderivative of t squared minus t. Let us say t cubed over 3 minus t squared over 2. And then we're just going to evaluate this from t equals 0 to t equals 2. So plug in 2, you should get 8 over 3 minus 4 over 2. And if we plug in 0, we're just going to get 0 minus 0, which is just going to be 0. So if we do the common denominators, we should get 16 minus 12, 4 over 6. Or in other words, 2 over 3. So here, since the velocity was meters per second, the displacement is going to end up being meters. So for part B, if we want to find the distance traveled, we're going to take the integral of the absolute value of t squared minus t. But we realize that from 0 to 1, this function is getting negative values, right? So the absolute value of t squared minus t is going to equal to t minus t squared in this interval. And from 1 to 2, since it's getting positive values, we can just take out the absolute values. It's just going to equal to t squared minus t. So I'm going to divide this into two integrals. First, I'm going to integrate from 0 to 1, and then from 1 to 2. So as we pointed out here, t squared minus t, since it's getting negative values, the absolute value of a negative number would be negative of that negative number. So here the absolute value is going to equal to just negative of t squared minus t. So that's going to be just t minus t squared. And t squared minus t is getting positive values here. So since it's getting positive values, the absolute value, we can just drop the absolute value. The absolute value of t squared minus t is going to equal to t squared minus t in here. Okay, so if we calculate again by fundamental term of calculus, I'm just going to distribute this negative. Integral of negative t squared is going to equal to negative t cubed over 3. And then I'm going to have positive t here. Integral of positive t is going to be t squared over 2. And we want to evaluate this from 0 to 1. And the integral of t squared minus t from 1 to 2 is going to be, let me go down, t cubed over 3 minus t squared over 2. And we're going to evaluate this from 1 to 2. So t from 1 to 2. So here we plug in 1 and 0. And for this part, I got the value 1 over 6. And for this part, we plug in 2 and 1 and take the difference. For that part, I got the value 5 over 6. So if I add these up, I just get 1. So as you can see, in the first part for displacement, we got 2 over 3, if I remember it correctly. And for part 2, the distance traveled ended up being larger, which we expected, because the object was going in an opposite direction, and this actually includes going back and forth. So it went in the negative direction, and it turned back and started going into the positive direction, right? So it probably passed through the original starting point. The displacement does not include the part where it went back and forth to the original point, whereas the distance traveled includes that as well. So we end up having something larger.